All right, good afternoon. How's everybody? All good? All right, so today we're going to talk about the aerodynamic thrust forces and moments. So these are the terms in the equations of motion. It looks like this. So this is the X force aerodynamic, X force thrust, rolling moment aerodynamic, rolling moment thrust, and of course we have the Y and the Z versions, and then the pitching moment and yawing moment versions of these as well. So we have the equations of motion. Now we need to detail these for an airplane. So we're talking about lift and drag and pitching moment. And the goal here is not to just develop the equations, but to understand the physics. In other words, what part of the airplane does what? What forces and moments does the vertical tail generate, and why is it there? So we'll come up with formulas and equations, but we also need to understand this. And so on the homework and on the exams, there will be questions like that. All right, so we've been using a body fixed axis system. And it's kind of arbitrary. We point X out the nose, Y out the right, Z down. I mean, we stick with that convention, but whether it's directly out the nose or up through the windshield or down a little bit, we could pick any way we want. And so we want to specify a specific axis system. I'm looking for my eraser. A specific axis system that has some advantages that make our job easier. All right, so you've seen this before. There's an axis system called the stability axis. And it's subscript with an S, like that. And the way this thing works is here's our airplane. Here's just the normal arbitrary XZ, and then Y is perpendicular. And the velocity of the air looks like that. And then here's the horizon. So extend this line in like that. So we would refer to this as the angle of attack. And then this is the pitch angle in the X, Y, Z axis, because theta is up from the horizon up to the X axis. And that's an Euler angle because we've taken the airplane and we've yawed it, and then we pitch up theta to get the X axis from the Earth fixed. And then this is what we call the flight path angle. Oh, and we put the 1 on it because it's steady state. So make sure you put a 1 on it. I forgot. So theta 1 is the steady state pitch angle. Alpha 1 is the steady state angle of attack. And what am I needing? Theta, or gamma. Steady state flight path. Right, so that's nothing new. So now we're going to say our stability axis is one where we point x into the relative wind. So draw an arrow like that and label it xs. And then z is going to be perpendicular to that, so it shifts down. In fact, that's not really that important, but this angle is alpha as well. And that's what we call our stability axis system. And it's nice because lift is perpendicular to that xs axis and drag is parallel. So that means if I want to find the force in the stability axis in the x direction, it's just minus the drag. So that makes it easy. And we'll detail this a little bit later, but that's why this axis is chosen, is because the lift and the drag are perpendicular and parallel to V infinity. So some features of this, just looking at the angles here, theta is gamma plus alpha. That's theta of the x-axis. And the theta of the stability x-axis, we're going to call theta 1s. So that's this deal here. That's the angle. It's still the pitch angle up to that axis. But it's just this. And notice that in the stability axis, gamma and theta are the same thing. So let me give you a minute if you're still drawing this picture, because this is an important picture to draw. I was just looking, so that shows up fairly clearly on the screen there. Kind of, sort of, okay. I wish I could make it bigger, but that's as good as it gets. Yeah?
The theta stability axis is equal to gamma 1.
Yep.
We have like both, why not smaller?
Well, you just look at the picture. This is gamma, and this is the angle up to the xs axis, which is how we define theta. So it's the same angle. But theta to the x-axis is all the way up to here, so that's equal to this plus that. It's just the geometry of the angles. If we defined another axis, call it the x-WSU axis for fun, there would be another theta up to that. And we'd have to define, well, what is this angle here? This is the theta, this is the, I don't know, the inclination, call this beta WSU, and so then this would be that plus that plus that. Again, all these axes are arbitrary, it's just the stability axis is one that is really helpful. I guess we could have called that the Wu-Shock axis system, I don't know. So don't add that to your notes unless you really want to. Okay, the other feature of this axis system is that in the stability axis, all of the air blows along the x-axis. And so the vertical, I mean, the forward speed is v infinity. And there is no w component. Right? W is the vertical speed in the z direction, and everything's perpendicular to that. So this also makes things somewhat easier, is that one of the velocity components is s. Now, it is possible to have a side velocity in this, although typically we'll start out with this picture here. All right, so what I want to show you next is a table in the book where essentially it talks about what variables affect what forces and moments. And this is not gospel, but this is typical. So let me share the screen on that. Yep.
If theta 1s and flight path angle the same, then why are we renaming it?
Hang on a second, I botched the share here. Sorry, I can't click and listen at the same time. All right, there I got it. Okay, you were saying?
If the theta 1s is equal to the flight path angle, then why are we renaming it?
We don't. Typically, we'll just talk about theta 1s, and we won't even worry about gamma. Because I guess you could call that gamma 1s, right? Well, it's just flight path angle. So in the equations, when we talk about flight path angle, we'll just put in theta. All right, so this is essentially a math model of what variable affects what. So here is, let me get my blue marker out. Here is the aerodynamic force in the x1s direction. We're going to say that it's going to depend upon alpha, not beta. So we're saying the side slip isn't going to change the drag. And so you could say, well, yeah, it can, but it has to be pretty large side slip. So for small side slip, we're not going to include beta in the equation. Ailerons, we're going to say that they don't add a whole lot of drag. They could, right? If you have really big ailerons and you deflect them a lot, but we're going to say they're small. Elevator, we're going to add a term in for this, but it's possible you could say that even an elevator deflection doesn't change the drag a lot, and the rudder doesn't. The same for like the Z force here. You're going to get lift due to alpha, but not beta. Not ailerons, but you will get some due to elevator, but not rudder. And the pitching moment is going to depend upon the angle of attack, but not beta. Ailerons, nope. Yes, definitely elevator, because an elevator generates a pitching moment. Rudder, not so much. And so those are the longitudinal forces and moments, because we say those depend upon alpha and elevator. And then the other set are what we call lateral directional. So it'd be this one, that one, and that one. And those depend upon beta. Aileron, although for the side force, we say the ailerons don't generate much side force, but they definitely generate rolling moment. And the side force due to the rudder does happen. The rudder can roll the airplane, And it definitely yaws the airplane, right? So we'll separate out our models based on these two separations because the variables are different between each model. This is in your book on page something or another. As soon as I find it. Page 67 in your textbook, 6-7. And you look at this, you go, well, there's no flaps. Well, we could add that. We just add another variable. If there's flaps, then we'll add another term for the flap. Lift spoilers, we could throw those in. If we add a bomb to our airplane, we'd have to throw in the effect of that. So every piece and part, we'd have to add in. So again, notice that there's not a whole lot of coupling between what I've called the green, the lateral directional, and the blue, which is the longitudinal. So alpha does not affect, say, the rolling moment. Yet you could probably think of a case where angle of attack would affect rolling moment. Like if you're stalled, right? One wingtip stalls before the other, you definitely get a rolling moment. So this model is good pre-stall. It's before stall. And again, like we said, it's for small side slip angles, because if you get a whole lot of side slip, then the lift from the right wing would be different than the left wing, and so you could get less lift or more lift due to beta there. All right, the other thing we assume is that we know the thrust. So we're just going to be given a thrust value, or we're going to say we need this much thrust. We're not going to worry about, well, what throttle setting maps to that thrust, or so much of how angle of attack and side slip affect thrust. We'll assume that we know that model. All right, so now we're going to go through the details of the formulas for each one of these. All right, so the first thing we're going to do is drag. All right, so we're doing the longitudinal forces and moments, and we're doing this in the stability axis. So that's the axis system that points into the wind. And so that means lift and drag are perpendicular and parallel to that axis system. And again, we talked about that before, it makes things easy. So the X1 force in the stability axis, aerodynamic, is the drag. The Z force is the negative of the lift. And then the pitching moment is still just a pitching moment. Doesn't matter which axis we're in. So MA1S is just the aerodynamic pitching moment. So do you like the subscripts that we get into in this stuff? I mean, this is typical of a lot of science and engineering. So we've got F, and the A stands for, what does A stand for? Aerodynamic, right? And what does X stand for? It means it's the x-axis. And the 1 means What does the 1 mean? Steady state. And the S at the end means stability axis, right? And if I replace the A with a T, then we get the thrust. And if I replace the Z, let's see, if I replace the X with a Z, then it's the Z force. If I replace it with a Y, then we're talking side force. So the subscripts help us keep track instead of like calling this one Ralph and this one George. Then we just have more stuff to remember, right? So we're good on that. So now we're going to talk about the drag. So we're going to talk about Ralph next. So that's the drag. So the negative of this then becomes FAX1S. And in fact, typically we get tired of writing the S on there. And so we'll just know that it's stability axis. So here is one math model. Keyword math model. This is an equation that approximates a formula for the drag. And the more you get into science and mathematics and well, not so much math because everything's defined, and engineering, you'll find out that everything is really just a model of what we can observe of the universe, and it's not the whole story, right? You have a model of the atom that has protons and neutrons and electrons that we picture as little things spinning around, right? But then you take chemistry and you learn that the electron's not really a particle per se. It's like a packet of energy that we can model as having a wavelength and a certain amount of energy, but even that's just a model of what's really going on. And no matter how deep you dig, you always find out, well, there's more that you don't know. It's just a model of what we can observe. All right, so this is one model that works well for designing aircraft. We're saying, okay, there's some parasitic drag. Then there's drag due to lift. If you could figure out a way to get rid of either one of those, you'd become rich. So start working, right? If you could figure out how to do anti-gravity so we don't get any drag by counteracting gravity, then you'd be good. Although I'm guessing it would take a lot of energy to do that. And then we separate out the drag due to the incidence angle of the horizontal tail, because it turns out that you can set the horizontal tail at a different angle than matching up exactly with the wings, so you could get some drag from that. And then when we deflect the elevator, oh, and put ones on all these because this is all steady state. And in that table I showed you, he neglected this. He said for small elevators, this is small, but I tend to write it in there so that we can include it if we want. But this thing, based on what we already know from aerodynamics, is an approximation of a drag polar. Because if you plot CD versus alpha, it's not a line, it's this thing. And so what we're saying here is that at a certain angle of attack, we run a slope through this, and then we get an intercept that's the CD0, and then the CD alpha is the slope of that thing. So if we are at a different steady state angle of attack, we have a different model. So maybe we call this alpha 1A, and then if we're at a different point on the polar, we have a different, so this is alpha 1A, it's alpha 1B, we have a different slope and a different intercept. And so if we can, maybe we don't want to use this linear model. We should have put linear in here. Maybe we want to do a drag polar, which is a parabolic. And if we have the drag polar and we can handle the nonlinearity in it, then we use that. If we want a linear model, then we use this. So this is option 1, or model 1. Option 2 is a drag polar. And it's done as a lift polar. And you've seen that before, CL squared over pi E AR. And then we could even make the drag of the elevator more fancy, but we'll just tack it on there. And you could match this to this if you want to, essentially by doing what we're talking about here. So if the drag polar is this curved thing, then you'd match the slope. You'd take the derivative of this thing with respect to alpha to get CD to alpha down here. And then you could set equality. You could set up so you could get the intercept just by setting it up equal to the drag at that point. So if you know the drag polar and you can't handle the nonlinear drag polar, then you can get CD alpha by just taking the derivative of this. And this is just a constant, right? That's the intercept of the drag polar. Notice there's a bar over here because it's going to be different. And then you get the derivative of this respect to alpha, and this is what depends on alpha. So if you know the lift curve slope of your airplane, then you can match your drag polar at a certain angle of attack to match this, because CL here depends on alpha. So you stick in your CL that corresponds to the alpha, that gives you your slope, and then you can set this equal to, you can set the two equations equal to each other to get your intercept. But typically, like if you're doing homework or on an exam, I will give you either the linear model or I'll give you the drag polar, and that will be what you use. And again, if you can and you have it, use the drag polar. If for some reason, and especially if we're Laplacing, you're going to need that linear model. And so we'll need the linear model to do that. All right, so what that means is now we have an equation that models how the drag varies with respect to angle of attack in the elevator and IH. All right, and this thing is in a table in the book, so I'm going to show you that next. This is page 93 in your book. And it's a table that has essentially vector and matrix formulas. And so the entry that we just did was the FAX. So this is the formula that I wrote up there. It's FAX is minus D, which is CD cube RS. And then here's the formula for CD that goes up in here. CD0, CD alpha, CDIH, CD delta E times this vector here. And I'll be happy when my touchscreen laptop comes in so I can do a better job of writing on this screen here. And so the next entry that we're going to do is the lift. And it's going to be CL0, CL alpha, CLIH, CL delta E. And you can see by the way that things are subscripted is that it's easy to remember and see what multiplies what, right? If you write this out, CL subscript alpha, you know that's going to multiply alpha. So that helps you keep track. All right, for the lift, we're going to have to add the lift of the wing plus the lift of the tail. And so that's going to make this a little more complicated. We're not just given the values, because if we want to build an airplane, we will build the wing up and we know what its lift curve slope is, build the tail up and we know what its lift curve slope is, and then we can estimate, do a better job than the drag polar where we're just given it as data. All right, I think it's time for a 3-minute break. Everybody stand up, jog your brain, get a drink of water, watch out for my tripod. Especially since a lot of you are sitting here staring at the screen, and I think it's good to get up and walk around. Thanks. Yeah. Oh, if you're asking about the homework, wait till we get back started, and that way everybody can benefit.
I'm just not sure, like, how do I recognize steady state terms?
All right, let's get started again. I was just looking at the news for the heck of it. Looks like the aviation news is a Russian jet violated NATO airspace while attempting to intercept a B-52 over the Black Sea. Interesting. It says a Russian military jet violated NATO airspace near the Danish island of Bornholm. Anybody been there? It's not showing where? Oh, it's because I'm not sharing the screen. Yeah, so it's just another incident. Who knows what'll happen? There aren't a whole lot of B-52s still flying, but they are ancient. For another what? Sorry, to do what?
There's open job openings in Oklahoma City and Boeing.
Yeah. So they're going to be around longer. All right, anyway, that's the exciting news for today. You had a question about the homework.
On the step 3, when we're supposed to take out the steady state terms,
Yep.
on the right hand side where I have NG, sine, P, cosine, all that stuff, I'm having trouble recognizing which one the steady state terms are.
He's asking, for you guys that are on Zoom, he's asking about steady state terms. How do you recognize them? You look at the variables and there are no perturbation variables in the term. And the other clue is look at the steady state equation that you're going to subtract out. Because you really don't have to identify the steady state terms. You just subtract that equation and it will knock out all the steady state terms.
Do you know where those equations are in the book?
The steady state equations, chapter 1. There's a big heading that says summary of steady state equations. And I showed that page on one of the lectures last week. Okay, any other questions, homework, or otherwise? When's that homework due?
Next
Tuesday, right?
Next week, yeah.
After the long weekend. So everybody do it before Friday night so that you can have a long weekend. Yeah, it's Labor Day weekend. They did not cancel Labor Day for this year. All right, airplane lift. So we write it in terms of its coefficient because that's how all of the data is presented. Multiply by Q and S, and that's the lift. So our linear math model we already looked at it. I showed it to you in that table with the matrix. Yeah, we already did that one. Z, there we go. Thank you. All right, so the way we build this up is we talk about the lift as being the sum of two independent lift sources, the wing, fuselage, and the horizontal tail. If we had a missile, we'd have to add that. If we had the space shuttle on top of our airplane, which is not flying anymore, we'd have to add that. So really what it is you just keep adding the lifts of each of the independent components. If there's an interaction between the two, then you have to add some extra terms to account for that, because you can imagine that the lift of the space shuttle being on top of the 747 is going to affect the lift of the main wing of the airplane, right? All right, so take this equation and write it in terms of coefficients, because we're going to coefficient everything, because that's how the aerodynamic model is. So the lift here is going to be replaced by CLQS. Lift of the wing fuselage is CL, wing fuselage, Q. S, and we're assuming the dynamic pressure of the entire airplane is the same as this for the wing, but it's possible that the tail could be in the downwash or the wash backwards from the fuselage. So we need to, I'll get it here. There could be a different dynamic pressure at the tail. You need to put an H there. And then of course the area of the tail is different, and the model of the lift that we use building up from the airfoil data is based on its own area. And so whereas for the drag, we pretty much stopped with the linear model that I gave you, we can fill in more pieces on this because we know how to aerodynamically model the lift of a wing based on the airfoil that it's made out of, how big it is, how much it tapers, and everything else. So we can put a little more of that information in. Maybe I should put my eraser chair up here. All right, so if we divide through by Q bar S, we can simplify things. And then here we get the CL of the wing fuselage, and then every time we have the tail stuff, we're multiplying by these ratios. And in this book, he often calls this A to H. because he gets tired of riding it. And most of the time, we'll just say that's 1. But we include it so that we can change it if there is a wake coming off the fuselage and wing that affects the horizontal tail. Okay, so number 1, we're going to do this. And number 2, we're going to do this. And then we're going to add them all together. Yeah. Which several people are talking, and with the mask and everything.
Variable that you just wrote, something.
Down at the bottom, that's eta. Sorry, it probably needs a longer tail on it, doesn't it? It's one of those letters that the Greek fraternities and sororities invented. No, it's a Greek letter. Yeah, please ask. If you see something you don't know what the heck it is, ask. Otherwise, you'll think about it all night, or maybe not.
So the lip of the missile and the slipper is space.
Yeah, those are just for fun. I didn't include those.
Oh, yeah.
I mean, we could, right? We could add the CL of the bomb and the CL of the space shuttle. But we're going to stick to this normal airplane. All right, so we're going to do number 1. And so there's the lift at 0 angle of attack. And there is the lift due to angle of attack. And you've seen that. We did that in 514. You do it in aerodynamics. We can, if we know the shape of the wing and the airfoil it's made out of, we can get these numbers. We can get this model. You have to go through that big formula that takes into account the aspect ratio and everything else. So it's easy to write, but there's a lot of work behind the scenes on this as well. And then the model for the horizontal tail, it's its own flying surface. So there will be some lift at 0 angle of attack at that. There will be some lift due to the angle of attack. And often, if you have a symmetrical tail, this ZL0 is 0, but not always. And then deflecting the elevator. Also affects also, sorry, I was checking some. Also affects the lift. But in this book, he does it a little different. Instead of writing CL subscript delta E for the horizontal tail, he includes this thing that's called the elevator effectiveness. So I need to talk a little bit about that.
Dr. Steck.
Sorry, it's the elevator angle of attack. Really what it does is it converts elevator degrees to alpha degrees. And it's the best way to explain that is to just do an example. So let's say we're in a wind tunnel just with our horizontal tail. And we do an alpha sweep at 0 elevator. So there is 0 elevator. And then we do another alpha sweep where we've deflected the elevator plus 10 degrees, which is trailing edge down, so we get more lift, right? And if we look at the increase here, it gives us the equivalent increase in lift as if we were at a different angle of attack. So here, let's say this is 5 degrees. And if we see the lift jump up due to the elevator and we go across, it's like we had no elevator, but we were at an angle of attack of 10 degrees. And that's what this tau sub e does, is it says, all right, it gives me how many effective angle of attack degrees I get from the elevator. It's not saying we're actually pitching the horizontal tail, it's just that's how much extra lift. And so for this case, tau sub e would be 10 minus 5, because that's the alpha distance, and then 10 minus 0. So it says that 10 degrees of elevator give you the same extra lift as 5 degrees of angle of attack. We don't have to do it that way, but that's how he does it in the book, so I'm going to be consistent with that. So pretty much we'll know what tau sub e is for our elevator. All right, so now we have to take these and go back up into this formula. You can see it's going to get complicated, right? And what's alpha h? Oh, this delta E1. Please put a 1 on that. Well, that's the angle of attack of the horizontal tail, so we need to talk about that some more. So it's going to be the angle of attack of the wing fuselage, or it's alpha 1. But then it could be affected by the tail setting angle. And in this book, IH is positive tilting up. In your 514 book, it was positive tilting down. So we have to subtract. So there's just that difference. So notice that we're saying we're adding this on. And then there could be some downwash. Because the wake vortex coming off the wing, right? And then we're going to add in our model. So our downwash model is, we're saying the downwash changes with angle of attack. And so there's our downwash model. And that's because those wingtip vortices at higher angles of attack are stronger. And they're affected by the angle of attack. So that's our model that we use for that. Pardon? What is it? Oh, thank you. No, downwash is down, so it's negative. Thank you. You're doing a good job looking through the poll. Oh, you're looking on the screen. Yeah. So you can see that this thing's gotten pretty complicated, right? Because this has got to go in down here. And then we got to multiply by the eta h sh over s. But fortunately, it's easy to group this stuff. I hope you're able to see green or red. Tell me which one shows up better. Okay, here's green. Oh, that's horrible. That's better, isn't it? Okay. Fortunately, we're going to be able to group stuff because some of this stuff is going to depend upon angle of attack. So we'll collect all those together. Some of it's going to depend upon IH. Some of it's going to depend upon elevator. And some of it's not going to depend on anything. So the stuff that doesn't depend on anything, that's all those constant terms in the front. And then we'll have a term that multiplies alpha and a term that multiplies elevator. So let's start with the ones that I circled in red. Actually, let's write out this CLH with it substituted in, because then it's going to be easier. So there's that. Then we got a whole bunch of stuff here. So there's where we plugged in alpha H there. And then we need to keep this formula here, because we're going to add this to this thing up here, all multiplied by SH over S and eta H. Right, remember that formula we had? CL, a wing fuselage, plus eta H, SH over S times CL of the horizontal tail. So first thing we're going to do is grab the terms that are constants. And although green doesn't show up all that hot, I think it'll show up for circling. So this term doesn't depend upon any variables. This term does not depend upon any variables. And this one doesn't either. So let's collect those three terms together first. So CL is CL0 So that's the three red terms. And that's the thing in our linear model for the lift that we call CL subscript 0, because it's the lift at 0 angle of attack, 0 elevator, 0 IH. All right, so now we grab the red terms. And those all multiply alpha. So let's grab them all, see if we can squeeze them into this bracket here. I'm going to sit down so I can better squeeze the terms. So that's CL alpha wing fuselage. That's the red term on the bottom. Here's all the horizontal tail stuff. And we got two of those. One of them is this term here. Guess I didn't circle these in red. And the other one's that term there. And notice the only difference between those is d epsilon by d alpha. So we can multiply by 1 and then this, and we can factor out and get that term there. So those are the red terms. Let me go ahead and redify them. So it's this term here. Those are the ones that came from up here, and then we still have this one there. And this thing is what we call, in our linear math model, CL alpha. So that's the lift curve slope of the entire airplane, the wing plus the horizontal tail. And then the next two are easy because we just have this term that depends upon IH, so I'll put a box around it. And then we have this term that depends upon elevator, so I'll put a diamond on that. And so we get a separate term for each one of those and we're done. So we have to add that to this. So I'm going to erase and continue above. So this is backwards math, but we're adding. Now we have a term that multiplies delta E. So that's the box term. And then the diamond, no, that's the diamond term, and then the box term is the next one.
Professor Steck.
So
I
again,
don't
all
know-
we're doing is rearranging the terms in those two equations. that
If
we
someone
added
can ask,
together.
what's the difference between the capital and the lowercase h?
And then this is what we call CL subscript delta E. This is what we call CL IH, and then those are the terms in that math model.
Dr. Steck,
Yeah. Me not being consistent. They're both horizontal tail. Somebody look in the book. What does he use?
Thanks, Austin.
And sometimes I think he changes, like if he writes VH. Let's say he uses lowercase h for CL. Looks like it's totally my problem. I should be using, he uses lowercase h, so everything should be lowercase. You're talking about here. So let's fix that, at least for now, until I forget again. I think the reason I write uppercase is it's easier to see when you're writing on the board, but this is what he does in the book. Sorry for the confusion. Did I miss any? Yep, up here. And as I showed you before, if you go back to that table, it's got the formula for CL is CL0, CL alpha alpha, CL IHIH, CL delta E delta E. And then in the book are these equations that allow you to detail out how to calculate each one of those terms. So that's it for today. Questions, comments? All right, we're headed in the right direction. Over the weekend, the COVID positive test rate was down to 8%. Although there's a lot of variability, it just depends on who shows up and what. But hopefully it keeps going down. All right, I'll see you guys on Thursday. Work on the homework. If there's any questions, let me know. If you need to Zoom me for office hours, shoot me an email. Otherwise, I have office hours listed on the syllabus.